The first official images of 3I Atlas have landed, and they are an electric shock. Against the velvet darkness of space, this pale shard hangs with an outline that stubbornly refuses to settle into anything familiar. Is it truly a long knife-edge profile, or a lopsided body with a faint, feathered halo? As if dust is being teased away by an invisible wind from 3I Atlas. Highlights flash and fade as the viewing angle shifts, not like a neat sphere, but like facets catching the sun. If this interstellar visitor truly is 3I Atlas, why does it look like this? Why do the textures seem to change with the light? And why does the glow of 3I Atlas bend in a direction that our physical intuition does not expect? Tonight, we will not rush past those questions. We will slow the 3I Atlas images down, peel back the processing steps, and ask, what is the light itself saying? We will follow the trail from raw pixels to calibrated truth, from brightness that rises and falls to the shape that must be causing it, from color that leans red or blue to the chemistry painting the body of 3I Atlas. By the end, the phrase "hard to believe" will not be a dismissal, but an invitation. Because the harder a thing like 3I Atlas is to believe, the better our science must become to prove it. We are looking at a traveler that almost certainly did not grow up under our sun. Its path appears to be open rather than closed, the kind of course followed by a body that falls in from the deep dark between stars and then departs again. Astronomers treat such a visitor as a rare natural experiment. For a brief season, we get to test how material forged in another planetary nursery reflects light, sheds, dust, and responds to heat. The object's name matters less than its story. What matters is that the light in these frames carries clues about origin, composition, and shape, if we learn how to read it without letting our hopes outrun the data. When people hear official images, they often imagine a single perfect photograph. In reality, official means something more disciplined. It means a chain of custody for the pixels, careful records of exposure time and filters, the removal of camera noise and optical blemishes, and the alignment of stars so that the object's motion can be measured rather than guessed. It means photometric calibration so that each brightness value can be compared from night to night, and astrometric solutions so that each point on the frame maps to a precise direction in the sky. That is different from the many heroic but uneven pictures that race across social feeds. Community images can be beautiful and sometimes capture a surprise first, yet they are a patchwork of lenses, sensors, processing choices, and weather. One stack may boost faint details, but invent ringing around bright stars. Another may use an aggressive denoise that erases a thin gas coma. Official releases aim to make those choices explicit and repeatable, so that a change in appearance from one day to the next is more likely to be a change in the object rather than a quirk of software or atmosphere. Caution is not a lack of imagination. It is a way to protect imagination from error. Early frames of a fast-moving, faint target can mislead the eye. A streak can mimic a tail. A glint can masquerade as a shiny, engineered surface. The viewing geometry changes from hour to hour, and with it, the phase angle that controls how rough surfaces scatter sunlight. Scientists slow the footage, compare filters, and model how a spinning, elongated body would make the brightness rise and fall. Only after those cross-checks do they let a headline claim step onto the stage. So, what are we looking at, truly? We are looking at sunlight filtered through dust that may carry ices and carbon-rich grains, at colors that tilt redder or bluer depending on grain size, at a light curve that hints at shape and spin, at a track through space that speaks of an origin beyond our planetary family. We are looking at a message written in photons, delivered from a place our spacecraft have not yet reached. The promise of these official images is simple and demanding. If we measure with care, the pictures will stop being unbelievable and begin to be exact. Astronomers begin with names, but the name is only the doorway to a fuller identity. When we say 3I/Atlas, we are pointing to a visitor that appears to come from beyond the Sun's gravitational family. Its path looks open rather than looped, a sign that it will sweep in and then leave for interstellar space again. Identity in astronomy starts with motion and light. Motion reveals the shape of the path, and light reveals what the surface and the surrounding dust are doing. From those two pillars, a portrait slowly develops, not a headline sketch, but a patient likeness drawn from repeated measures. The first question is classification. Is this a comet, an asteroid, or something that blurs the line between them? Comets carry volatile ices that can sublimate into gas and dust when heated, creating a coma and sometimes one or more tails. Asteroids are usually drier, darker rocks that keep a tighter hold on their dust. 3I may show hints of a faint halo or a directed haze that leans away from the sun, yet it also shows stretches of behavior that feel inert and rocky. A hybrid is not a cop-out. Nature is messy, and many small bodies are transitional. Brightness is the next anchor. The apparent magnitude tells us how much light reaches our detectors from Earth's vantage, but the more telling quantity is how that brightness changes with time. A steady rise and fall can signal a rotating body whose shape is elongated, so that broad and narrow sides take turns facing the sun and the observer. A random flicker may point to jets of gas that switch on and off, or to clumps of dust that briefly reflect extra sunlight. By building a careful light curve, night after night, observers translate flicker into spin, and spin into clues about shape. Color helps to separate ice, rock, and carbon-rich grains. Through different filters, the object may lean slightly red if the dust is dominated by larger grains or by complex organics, or lean slightly blue if very fine particles dominate. Mild color changes with viewing angle, known as phase effects, can also betray a textured surface rather than a polished one. Spectra sharpen the picture by revealing absorption and emission features from water ice, carbon monoxide, cyanide, or silicate dust. None of these signals shout, they whisper, and they must be heard above the noise of the sky and the instrument. Geometry matters as much as chemistry. The phase angle, the angle between sun, object, and observer, controls how shadows pool in surface cracks and how forward scattered sunlight brightens thin dust. At small phase angles, the coma can look fat and symmetric, while at larger angles, it can stretch and skew, tricking the eye into seeing structure where there is only light geometry. Distance plays along, setting the scale of each pixel and the tolerances for tracking the swift motion across the star field. Good identity work begins by correcting for these changing vantage points. Environment completes the dossier. 3I is moving through a volume of space that is not empty. Solar wind, ultraviolet light, and micrometeoroids all work as sculptors. If outgassing is present, a gentle non-gravitational push can change the track by a measurable sliver, reinforcing the comet-like classification. If the track stays purely gravitational, the pendulum may swing toward an asteroid like nature. Either way, we are watching a body that did not form in our planetary nursery, and that fact alone promises unfamiliar mixtures of ice, rock, and dust. Put together, the identity is a living hypothesis. At this hour, 3I/Atlas reads as a likely comet leaning toward the dry and quiet end of the spectrum, or a rocky body that still carries pockets of volatile ice that wake under sunlight. Its light curve suggests rotation and perhaps an elongated form. Its color hints at processed dust touched by cosmic rays during a long interstellar voyage. This is the honest answer to who it is. A guest from another cradle of worlds, speaking in light about where it has been and what it is made of, while it passes through our sky for a brief and generous visit. Discovery begins not with a shout, but with a thin line of pixels that refuses to behave like a familiar neighbor. On a calm night, an automated survey flags a moving point whose path does not match the family of near-Earth asteroids. The alert travels to human eyes, and within hours, a watcher confirms that the drift is real and not a bad subtraction of starlight. The candidate is posted to public boards where comet and asteroid hunters gather. A provisional tag appears beside it, and the clock starts. If this is interstellar, the window to prove it will be brief. Follow-up is the heartbeat of certainty. Independent teams swing telescopes to the coordinates and report positions measured against the star field. Each precise dot on a new frame tightens the arc of the path, turning a guess into a track. The survey origin offers raw frames so others can verify that nothing in the camera or the software is creating a phantom. Weather cooperates in some places and ruins attempts in others, yet the chain of custody grows. With each successful measure, the probability that this is a real object climbs from suspicion to confidence. Astrometry is joined by photometry, the careful weighing of light. Observers report an apparent brightness and the color through standard filters. A trend emerges. The light is faint but coherent, varying in a way that could be the signature of spin. The lack or presence of a soft haze is logged because a coma announces volatile ices, while a crisp point favors a drier body. These numbers are small and the errors are real, so teams cross-check calibrations against field stars. The goal is simple: to know that a change in light is in the sky and not in the instrument. At the center of the web, the Minor Planet Clearinghouse collects each position and computes fresh orbits. Early solutions are wobbly because the arc is short, but the fits steadily prefer a path that does not close. The word eccentricity enters the conversation, and the crucial phrase appears: greater than 1. That is the mathematical way to say the object is not bound to the sun. No single night can carry that claim alone. It takes nights stitched together across longitudes to turn a hint into a statement and a statement into a conclusion. The call goes out for spectra. A few observatories with larger mirrors and stable spectrographs win brief windows to split the light by wavelength. Even a low signal spectrum can reveal whether common comet gases are present. Meanwhile, image processors stack sequences to bring out any faint tail aligned away from the sun. Some stacks show a whisper of asymmetry, others do not, and the debate stays healthy. Through it all, new astrometry keeps arriving, shrinking uncertainties in the predicted sky path so that more instruments can lock on. Archivists and enthusiasts begin a search for pre-covery, the art of finding the object on older images taken before anyone knew to look. This is detective work with chance as a partner. A lucky frame taken days earlier might hold a dim echo that, once measured, lengthens the observational arc. Each pre-covery point sharpens every parameter: the time of closest approach, the distance, the expected brightness, the rate of motion. With a longer arc, the interstellar nature hardens from likely to almost certain, and the community adjusts its observing plans accordingly. Finally, confirmation arrives not as a single drama, but as a steady, quiet chorus. The orbit solution settles on an open track. The brightness behavior is consistent from telescope to telescope. Any small non-gravitational push is bounded and accounted for. A formal circular is issued, and the designation becomes part of the record that future students will read. What began as a stubborn smear has become a named visitor with a documented journey. The discovery phase closes, and the deeper work begins. To ask what this traveler is made of, how it spins, and what its brief passage can teach us about worlds that formed beneath another sun. Official does not mean pretty first, it means trustworthy first. An official image begins long before a shutter opens, with a plan that matches instrument to target. Telescopes are chosen for aperture, field of view, and tracking that can follow a fast mover across the stars. Cameras are picked for stable response and low noise. Filters define which colors of light pass and which are blocked. Exposure times are tested so the object is bright enough to measure, but not smeared into a streak. Every choice is written down, because traceable choices are the backbone of credibility. Raw capture is a dance between sky and silicon. The mount must track at the object's own motion rather than the slow drift of background stars. Short exposures freeze the shape but cost precious photons, while long exposures gather light at the risk of blur. To solve this, observers take many frames and later align and stack them in the object's frame of rest. Small offsets called dithers help reject hot pixels and cosmetic flaws. The goal is simple. Build a deep image that still behaves like a truthful measurement, not a painting. Before any science can be trusted, the camera's quirks must be removed. Bias frames record the baseline electronic offset. Dark frames measure thermally generated noise at the same exposure and temperature. Flat fields map uneven sensitivity and dust shadows across the detector. These are combined into master frames and applied to every raw exposure. Subtract bias and dark, then divide by the flat. Vignetting fades, dust rings vanish, and pixel-to-pixel response evens out. What remains is closer to the sky and further from the camera. Now, the image must learn the language of numbers that others can compare. Photometric calibration turns counts into brightness with physical meaning. Standard stars in the same field set a 0 point. Atmospheric extinction is measured so that thinner or thicker air can be corrected. Color terms adjust small biases between filter systems. With this, a brightness measured tonight can be compared with one measured on another telescope tomorrow. A curve of light over time becomes a reliable witness rather than a loose impression. Position is the other half of truth. Astrometric solving matches the pattern of stars to a sky catalog and writes a world coordinate system into the image. Optical distortions are fit and removed so that one pixel corresponds to a known angle. The object's center is then measured frame by frame, not by eye, but by fitting the light profile. Those positions turn into a precise track across the heavens. With that track, orbits tighten, predictions sharpen, and follow-up windows become real instead of hopeful. Even the cleanest pipeline can invent beauty that is not there. Aggressive sharpening can draw bright halos around stars and carve false edges on a faint coma. Heavy denoising can erase a thin gas tail. Overly stretched contrast can suggest metallic glints where only noise lives. Official processing guards against these traps with tests. Does the feature persist in different filters, on different telescopes, and under different algorithms. When a detail fades under such checks, it is flagged as an artifact, not a discovery. Only after these steps does an image earn the label official release. The final frame is stacked and calibrated, annotated with scale bars and filter notes, and accompanied by metadata that documents the path from photons to pixels. A press-friendly render may sit beside a science-grade product, but the science-grade version remains the reference. It is not designed to thrill the eye. It is designed to carry weight. When we say the new official images are hard to believe, we mean they are extraordinary and yet accountable, because every pixel can show its work. Point 1 is shape, inferred not from a crisp outline, but from the rise and fall of light. When brightness climbs and sinks with a steady rhythm, it is as if the object is turning a long side and then a narrow edge toward us. That is the signature of an elongated body, or of a flat, slab-like geometry that flashes as it rolls. Sometimes the rhythm splits and wobbles, hinting at a tumble that is not a simple spin, but a complex, non-principal dance. The unbelievable part is how strongly the light curve suggests a geometry that our intuition rarely expects from a natural rock wandering between stars. Yet geometry alone does not explain the drama. The viewing angle changes night by night, and with it, the way surfaces reflect sunlight. At small phase angles, rough terrain can look muted and generous, while at larger angles, the same facets throw sharp glints that punch above their size. These phase effects can turn a modest protrusion into a lighthouse pulse on the detector. The hard-to-believe moments arrive when a tiny change in angle makes a large change in apparent shape, tempting the eye to imagine fixed structures that may be mostly a play of light. Point 2 is surface texture, and it lives in the way the object reflects light in directions that are not uniform. A truly matte world would glow evenly like a charcoal ember. This traveler does not. There are brief surges, little mirror-like accents, and slashes of brightness that sweep across frames as if some faces are polished or ice-glazed. Forward scattering by fine dust can amplify this effect, so that grains hovering near the surface act like a subtle lens. A patchwork of crust, porous regolith, and frost would explain the capricious highlights that look engineered but are born of weathered geology. Texture also means shadow. A field of pits, ridges, and ledges can cast miniature nights that migrate with rotation. Under shallow sunlight, those shadows lengthen and knit together, darkening a hemisphere beyond expectation. Under high noon, they retreat and reveal pale interiors that reflect more strongly. These contrasts can conjure the illusion of stripes, panels, or ribs. The mind leans toward artificial symmetries, but the more cautious reading is a natural surface that carries scars from ancient collisions and long exposure to radiation, each scar adding a wrinkle to the map of brightness. Point 3 is activity, the faint breath of a coma and the suggestion of a tail that will not sit politely on the line away from the sun. In some official stacks, there is a haze that leans, not straight but skewed, as if jets are venting from specific latitudes and being bent by rotation and wind. The axis of that haze can wander between nights, making it look like the whole object has pivoted. The unbelievable feeling comes from this asymmetry. We expect a gentle, symmetric cloud. Instead, we glimpse a living plume, directional and changeable, like steam from vents on a turning kettle. The coma's behavior also challenges habits. A barely present halo can thicken when heating crosses a threshold, then thin again as the active patch rotates out of sunlight. Fine grains accelerate and spread, while heavier clumps lag and fall behind along the path. Solar wind can comb the smallest particles into a fan that is not perfectly anti-solar. Put together, the scene resembles a painter flicking a brush, each flick leaving a different orientation. What seems like a rigid tale becomes a layered record of hours and days, written in dust and light. Across all 3 points, the guard against self-deception is replication. If a bright streak shows in one filter but vanishes in another, it is suspect. If a glint appears on one telescope but not on a sister instrument under similar conditions, it may be processing. The features that survive cross-checks are the ones that earn belief. The persistent double peak in the light curve, the repeating pulse at a particular rotation phase, the coma skew that returns when the geometry repeats. Unbelievable turns to extraordinary when a pattern comes back for a second and third audition. Even after caution, one vision remains. A visitor shaped far from our sun, perhaps stretched or flattened by ancient forces, its skin a mosaic of crust, frost, and dust, throwing lances of light when angles align. Around it, a breath-thin atmosphere blooms and collapses as sunlight prowls across its turning face, leaving a tilted veil that flows with solar wind. This is not the neat sphere of textbook sketches. It is a complicated shard of another nursery, carrying weather, scars, and habits from a different dawn. Why call these 3 points hard to believe? Because each runs against a comfortable picture of what small bodies should look like. The universe is under no obligation to meet our expectations. The lesson of morphology is humility paired with discipline. When brightness beats like a drum, when highlights flash like a mirror, when a tail leans like a windswept flag, the images ask us to look twice, measure 3 times, and then let the strange be the teacher. In that posture, disbelief becomes the first step toward understanding. Spectroscopy turns pictures into sentences. Instead of guessing from shape alone, we ask what wavelengths are present and which are missing, because missing light often marks a specific molecule that has swallowed it. A smooth continuum suggests sunlight reflected by dust, while carved notches and delicate peaks reveal ices and gases. Water ice leaves familiar fingerprints, so do carbon-bearing species that can shed light when warmed. Even a thin coma can glow in narrow features, while solid grains write broader curves. In this way, color becomes chemistry, and chemistry becomes a history lesson written in light. Start with reflectance, the ratio of light returned to light received, measured through filters that span ultraviolet, visible, and near-infrared. If the curve leans gently upward toward longer wavelengths, we say it is red, often a sign of complex organics baked and irradiated into dark residues. If the curve lies flatter, fine mineral grains or fresher ice can be at work. A sudden dip can betray silicate bonds, while a soft shoulder can hint at frost mantles. None of these clues shout on their own. Their power comes from a consistent pattern that repeats across nights and instruments. Color does not stand still. It shifts with geometry. When the sun, the object, and the observer line up in different ways, the phase angle changes. Rough surfaces favor forward scattering and can appear redder as the angle grows, a behavior called phase reddening. Very fine grains can do the opposite and wash a spectrum bluer under certain views. These effects matter because they keep us from blaming chemistry for tricks of light. By watching color through a sweep of angles, we can peel away geometry and leave a truer map of what the grains are made of and how they are arranged. Gas, when present, speaks in narrow lines. Cyanide glows in the blue-green. Carbon monoxide and carbon dioxide leave imprints in the infrared, and water can show both in emission from the coma and in absorption when frozen on grains. A quiet spectrum with few lines leans toward a rocky or devolatilised surface. A busy spectrum signals active ices. But nature loves the middle ground. A mostly dusty traveler can still carry pockets of ice that wake only when sunlight falls just right, writing a part-time signature that careful observers can catch in short windows. Dust tells its own story through grain size and composition. Silicate particles scatter light in a way that can raise a gentle hill across the red and near infrared, while complex organics flatten the view and deepen the darkness. Coarse grains mute spectral structure, as if many small voices were blended into one low tone. Very fine grains carve sharper shapes. Space weathering, driven by radiation and tiny impacts during a long interstellar cruise, can redden and darken the surface skin, building a crust that hides fresher material until activity chips it away. Comparison makes meaning. The first interstellar visitor was oddly red and showed little obvious gas, with brightness changes that suggested an elongated shape and possibly a smooth skin. The second interstellar visitor behaved more like a classical comet, with strong gas features and a dust-rich tail. Our new traveler appears to sit between those poles. Its colors lean warm but not extreme. Its spectral hints of volatile material are modest and episodic, and its reflectance shape resembles processed cometary dust more than bare stone, though the door to hybrid nature remains open. Put together, spectroscopy and color sketch a layered body. A weathered rind darkened by radiation, patches where ice still lingers in sheltered pores, and a cloud of dust whose grains range from powder to grit. When sunlight shifts and warms a vulnerable patch, faint gas stirs, small particles lift, and the spectrum grows a temporary voice. When the angle changes back, the voice softens, and the dust alone speaks. The hard-to-believe images become easier to trust because the colors and the lines explain why the light looks the way it does and what matter stands behind it. An ordinary minor body loops the sun like a bead on a string. 3 I/Atlas does not. Its path is open, the geometric sign of a traveler that will sweep through our neighborhood and then be gone. Astronomers describe this with a single idea. The shape of the orbit is more than a circle or an ellipse. It is a curve that never closes. That is why the track bends under the sun's pull, yet never locks into a family of comets or asteroids. We are watching a brief negotiation with gravity, a handshake rather than a lifelong bond. Speed and direction deepen the strangeness. The object arrives from a tilted lane, cutting across the plane where most planets keep their traffic. Solar gravity curves the path toward a closest approach, the moment called perihelion, but cannot claim the visitor. After the swing, the outbound leg rises on a new heading, carrying away a memory of the sun's tug as a gentle deflection. This geometry matters because even small errors in early measurements can snowball, pushing predicted positions off by more than a telescope's narrow field. On top of gravity rides a set of quieter forces that can shove the orbit by a whisper and still matter. Jets of gas that vent from sunlit patches act like tiny thrusters, a non-gravitational push that can move the object outward or sideways by a trace each hour. Sunlight itself can add a thermal nudge as warm surfaces re-radiate heat unevenly, a cousin of the Yarkovsky effect known to sculpt the paths of small dark rocks. These pushes are small in instant, but large in consequence when integrated across many days. To tell which forces are at work, astronomers live inside the details. They collect positions night after night from different longitudes, stitching a chain of precise dots against the star field. A pure gravity model is fit first. If the leftover errors line up in a pattern, a gentle thrust term is added, pointing either away from the sun as outgassing would do, or along the track as thermal recoil would prefer. When the pattern of errors collapses toward noise, the model has found a truer shape for the invisible forces steering the flight. These subtleties have practical stakes. A fast mover can slide across a detector so quickly that a long exposure turns it into a streak and smears away useful signal. Track too slowly and you lose sharpness. Track too fast and you blur the background stars that anchor astrometry. Near closest approach, the rate of motion can change rapidly, and the phase angle swings, altering how surfaces scatter light. Schedulers must juggle exposure time, tracking rate, and filter choice so that a precious window produces measurements rather than pretty but empty pictures. Prediction becomes a living thing rather than a single chart. Each new measurement tightens the corridor of likely future positions, allowing larger telescopes to pounce with narrow fields and specialized instruments. Miss a night, and the corridor widens. Catch a pre-covery image from an earlier date, and the corridor shrinks. The dance continues across observatories. One site measures position, while another captures spectra, and a third watches the light curve build a rhythm that encodes spin. Coordination turns minutes of sky time into a fuller portrait. Direction after departure whispers about origin. The velocity far from the sun, corrected for our planet's motion, traces back to a lane in the local star flow. That vector is not a passport stamp, but it hints at neighborhoods where the object might have been flung free long ago. If non-gravitational forces are modest, that backtracing is cleaner. If activity is strong, the outbound compass drifts a little. Either way, the path is a letter from another cradle of worlds, bent by our star and then restored to the great between. In the end, the unusual track is not just a curiosity. It is a laboratory that links grain-scale physics to star-scale navigation. Outgassing turns geology into propulsion. Thermal recoil turns sunlight into steering. Gravity writes the broad sentence, and subtle forces edit the punctuation. By reading that sentence with care, we learn how to forecast the next frame, where to point the next mirror, and how to set the next exposure. The sky rewards that discipline with truth, and a traveler that once seemed unpredictable becomes a teacher of precise motion. The first interstellar visitor, Oumuamua, arrived like a riddle wrapped in silence. It showed no obvious coma, no easy plume to mark it as an active comet, yet its brightness rose and fell in a way that hinted at an elongated or perhaps flattened shape. The light curve behaved as if a long body were tumbling, turning broad and narrow faces to the sun. Then came the greater surprise, a tiny but measurable push that could not be explained by gravity alone. The effect was small, but across many days it mattered, and it set the stage for years of debate about ice, dust, and the possibility of unfamiliar physics. Borisov, the second interstellar traveler, could not have been more different in its first impression. It wore a textbook coma and a dust-rich tail from the start, the very signature that Oumuamua lacked. Spectra showed familiar comet gases, and images revealed a steady, symmetric outflow that behaved as expected under sunlight and solar wind. If Oumuamua was a whisper, Borisov was a clear voice speaking the language of comets. Its behavior anchored the idea that interstellar visitors can look very much like the comet families we already know, even if they come from far beyond our planetary nursery. Shape sits at the center of the comparison. With Oumuamua, we infer geometry from light rather than from a resolved outline. The deep swings in brightness encourage models of a stretched or slab-like body, possibly tumbling in a non-principal rotation. That inference is delicate because it leans on how light scatters from rough surfaces at changing phase angles. With Borisov, the solid nucleus was never cleanly resolved either, but the presence of a coma means that the light we saw was dominated by dust and gas. The nucleus could therefore be more ordinary in shape, while the surrounding envelope did the talking. Activity is the next fork in the road. Oumuamua behaved like a quiet rock, yet displayed a non-gravitational push that many explain with invisible outgassing of very volatile ices or with exotic dust-driven drag. Others have explored thermal recoil as an aid, where sunlight heats one side and the re-radiated energy acts like a tiny thruster. Borisov needs no such subtlety. Its active jets and abundant dust provide a straightforward source of outward push, and its motion can be described by the familiar playbook of comet physics. In that sense, Borisov reassured, while Oumuamua provoked. From these two portraits, we carry practical lessons that matter for any new visitor. We learned how easily viewing geometry can fake structure, and how crucial it is to publish pipelines, calibration steps, and uncertainties. We learned that small non-gravitational forces can accumulate into meaningful orbital shifts. We learned the value of official images and traceable spectra that can be reproduced by other teams. Oumuamua taught humility about inference. Borisov taught confidence in methods that have served comet science for decades. Together they built a toolkit for the next object across the border. Into that context, we place the current traveler, sometimes called 3I/Atlas. It appears to borrow traits from both elders. Like Oumuamua, it tempts modelers with light curves that hint at elongation and with surface behavior that depends strongly on angle. Like Borisov, it shows signs of activity, though faint and changeable, that can skew a tail and seed a thin coma. If the first visitor was a question and the second was an answer, this one feels like a conversation between them. Against that backdrop, the new official images do not just amaze the eye. They help us test which lessons from the first two travelers truly generalize, and which must be rewritten for a sky that keeps surprising us. The question sounds simple and feels thrilling. Could a visitor from between the stars be a crafted machine rather than a carved rock? Science meets that thrill with a steady rule. Extraordinary claims require extraordinary evidence. We begin by asking whether ordinary physics can explain what we see. If natural processes can account for the shape hinted by the light curve, the odd glints, and the thin haze that waxes and wanes, then natural remains the leading story. The burden of proof sits squarely on any artificial idea to explain not only the drama, but every quiet detail along the way. First come the geometric tests. A manufactured object often shows sharp symmetries, repeating edges, or planar faces that keep fixed proportions as viewing angle changes. A natural shard tends to mix curves, pits, and ledges that rearrange in complex ways under changing light. We watch the light curve for steady, repeated rhythms that match a rotating, elongated body rather than a rigid panel. We map how highlights migrate with the phase angle. If the bright spots track roughness and frost rather than hardware, like straight struts or grids, the balance tilts toward nature. Reflectance and color deepen the check. Metals and engineered coatings reflect in ways that produce narrow, coherent flashes and stable color signatures. Weathered dust and porous crust scatter in a broader, messier fashion, with phase reddening and forward scattering that follow known laws. If spectra whisper of water ice, carbon-bearing gases, and silicate dust, and if those signals rise when sunlight strikes certain regions, then vents and frost explain the story without invoking design. A faint, skewed coma that grows and shrinks with heating is the signature of geology, not circuitry. Orbit and propulsion are the hardest gate. A true craft might hold or change course with continuous thrust or discrete burns. A natural body follows gravity plus tiny pushes from outgassing and thermal recoil. We fit a pure gravity path, then add the gentlest non-gravitational terms allowed by sublimating ice and uneven heating. If those modest terms collapse the residual errors and bring nights of data into harmony, there is no need to imagine engines. We also look for radio beacons, repeating modulations, or deliberate attitude control. Silence favors a natural traveler. What would it take to overturn that verdict? Multiple, independent detections of features that cannot arise from rock, ice, and dust. Polarization patterns that match polished panels rather than grains. Radar echoes showing flat, rectilinear facets. Thermal maps with heat sources unrelated to sunlight. A rotation state that holds a fixed orientation against known torques. Persistent, identical glints at the same angles across filters and telescopes. Until such tests reveal a fingerprint of intention, the official images, careful spectra, and well-fit dynamics argue that the unbelievable is not unnatural. It is simply the universe, stranger and richer than our first guess. Curiosity is only the spark. Capability is the firebreak. Each interstellar visitor reminds us that discovery is a race against a moving sky. The practical lesson is simple and demanding. If we want truth, we must build systems that can find, confirm, and characterize fast movers while the window is still open. That means wider sky coverage, quicker cadence, and smarter triage so that faint, high-speed tracks do not slip through the cracks. Wonder brings the audience. Engineering keeps the promise. Surveys are the first line of defense and the first line of insight. Wide-field telescopes need schedules that sweep the sky often enough to catch objects that cross a frame in minutes, not hours. Sensitivity matters, but cadence matters just as much. Software must recognize streaks that are not satellites and link them across frames into a tracklet worth an alert. The same network that protects Earth from near-planet objects can be tuned to flag interstellar lanes, because the physics of fast, unbound motion leaves a recognizable fingerprint if we look for it on purpose. The second lesson is about golden windows. Every target offers brief alignments when geometry, distance, and phase angle all cooperate. Map those windows in advance, and they appear like warm patches on a night sea. When an alert fires, schedulers can slide telescopes into those patches to squeeze out the most information per minute. Because weather, daylight, and instrument limits are local, only a global network can keep the chain unbroken. Handoffs from east to west and from north to south turn scattered nights into a continuous film. Pipelines are as important as mirrors. Official images earn trust because their path from photons to pixels is documented. We need that discipline at scale. Open alerts, shared calibration stars, common formats, and immediate posting of raw and reduced frames with uncertainty bars. Machine learning can sort the flood, but it must be yoked to transparent checks so that a clever algorithm does not become a single point of failure. Citizen astronomers can add sharp eyes and flexible time, provided their work plugs into standards that make each contribution comparable. Follow-up is the art of extracting every last clue. Rapid spectroscopy can tell whether faint activity is present before it fades. Radar, when geometry allows, pins down distance and speed with authority and can even hint at shape. High-speed photometry builds a light curve that turns flicker into spin. If agencies pursue ready-to-launch interceptors, even small spacecraft could perform a flyby on short notice, carrying a narrow suite of instruments designed for fast, high-phase encounters. Readiness here is measured in hours and days, not in seasons. Planetary defense gains directly from this practice. Even if interstellar visitors are unlikely to threaten Earth, the same tools model risk for near-planet objects on awkward paths. Better astrometry tightens impact probability cones. Ensemble simulations map corridors where a strike would fall if it were to occur, driving sensible decisions about additional observations. Tabletop exercises that rehearse communication, scheduling, and uncertainty updates turn potential panic into choreography. Precision, not drama, is the soul of safety. Finally, there is stewardship. Explain what we know, what we do not, and what we are doing next. Clear language about uncertainty builds public trust and keeps speculation from outrunning data. Funding should reward the dull, essential parts of the chain: maintenance, calibration, archiving, because glamour without groundwork fails when it matters. The lesson of these official images is that belief can be earned. With a vigilant survey network, coordinated follow-up, and honest communication, we turn brief, unbelievable apparitions into durable knowledge and a calmer, safer sky. A flyby is the boldest form of modesty. Accept that we cannot slow a stranger from the deep, but refuse to let it pass unseen. The interceptor idea is simple in spirit and ruthless in execution. Keep a small spacecraft fueled, tested, and waiting where launch energy is favorable. The moment an interstellar target is confirmed, the craft pivots from standby to sprint. A kick stage supplies the final delta V, and the probe rides a narrow corridor to arrive within a whisker of closest approach. Speed is an enemy of comfort, but a friend of discovery, if we prepare for it in advance. Readiness is the true propulsion. Traditional missions take years to bend hardware and software into harmony. An interceptor trades bespoke elegance for a kit of proven parts that can live on the shelf. Attitude control, navigation cameras, star trackers, sun sensors, radios, power, and computing must speak to one another on day one. Autonomy is not optional. Light time delays and the violence of a high-phase encounter mean the craft must aim, focus, expose, and protect itself without waiting for Earth. Practice on simulated targets until the sequence is muscle memory baked into code. The budget of motion rules everything. Delta V is the currency, and time to target is the inflation that steals its value. Prepositioning helps. A craft staged in a high-energy orbit can pivot more quickly than one that must first climb from the surface through thick air. Solar electric propulsion can bank gentle thrust over long months, while a solid kick stage can deliver a single decisive push when the window opens. Each kilogram spent on structure or margin is a kilogram not spent on fuel or instruments, so discipline becomes design. What would we bring to this knife-edge meeting? A narrow-angle camera with a fast, clean lens to seize sub-second frames before blur devours detail. A context imager to catch dust and tail geometry at wider scales. A compact infrared spectrometer to read ices and silicates under brutal lighting. A dust counter or microanalyzer to taste the grains if the geometry allows. A simple magnetometer if mass permits, because charged dust and solar wind write their own signatures. Every instrument must be radiation tolerant, low mass, and greedy for photons. Operations at speed require a choreography of light and shadow. As the craft closes, the phase angle swings, and the surface flips from night to day to a blinding crescent. The exposure ladder must step smoothly from long, faint frames to short, protective snapshots. Image compression must be tuned in advance, so that the best data squeezes through a narrow downlink before the target shrinks back into distance. A shield or smart pointing plan must keep the sun from burning the detectors, even as we hunt for the thin veil of coma and the texture of the nucleus. Risk cannot be erased, it can only be tamed. A last-minute trajectory update may be needed when new astrometry tightens the corridor. A safe mode entered at the wrong moment could cost the encounter. The answer is rehearsal and graceful failure. Redundant timelines, cross-checks between navigation camera and star tracker, and an onboard governor that refuses unsafe commands near closest approach. For the price of accepting danger, the payoff is a set of images and spectra that no telescope on Earth can match. A brief, blazing diary entry written at a range measured in heartbeats. The reward outlives the rush. A few minutes of sharp frames can anchor shape models, refine rotation states, and resolve the scale of surface blocks and pits. A handful of spectra can pin down which ices are awake and which are locked in shadow. Even a sparse dust count can set limits on grain sizes and ejection speeds. And perhaps most important, the playbook becomes real. A tested path from alert to encounter that future missions can follow. A flyby is not a gamble for spectacle. It is the fastest way to turn the unbelievable into the measured, and to meet a traveler halfway between mystery and knowledge. Official images do more than settle arguments, they reset feelings. When a frame arrives with its calibration steps laid bare, the picture carries both beauty and authority. People can let wonder in without bracing for a later correction. The object stops being a rumor carried by rumor and becomes a presence that anyone can visit again and again with the same result. That reliability changes the mood. Awe becomes steadier, quieter, and deeper. The sky is no longer a distant rumor mill. It is a place we can know together, with shared rules and shared light. This is where citizen science blooms. Backyard telescopes, school observatories, and small community domes do not replace the giants, they complete them. When a coordinated alert goes out, 1,000 small mirrors turn toward the same sliver of sky. Each contributes a little, and together those little pieces lengthen the movie and enrich the color. The act of joining the watch matters as much as the data. It is a lesson that participation is possible, that the border between expert and enthusiast is a bridge, not a wall, and that discovery can be a public craft. Shared observation rewrites our idea of time. A visitor that will never return can feel like a loss, but a threaded chain of images gathered by many hands turns absence into memory with weight. People remember where they were when the first streak was confirmed, how the haze tilted on a particular night, how a glint appeared just before dawn. The story lives not only in a press release, but in lived moments under cold air and quiet stars. That memory is communal. It is a kind of folk history written in photons and kept in thousands of minds. The traveler is more than an object. It is a mirror. We project hopes of encounter and fears of the unknown onto a shard of ice and dust, and then we watch those feelings bend under the force of measurement. The metaphor is simple and generous. A stranger crosses our home, and we learn to welcome without fantasy and to question without cynicism. The discipline required to read the light becomes an ethic for public life. Patience, transparency, replication, and the courage to admit uncertainty become shared virtues, not just lab habits. Art and science meet in these moments. Composers score the slow swing of the orbit. Painters interpret the grain of the light. Writers borrow the language of dust and tail to talk about departure and return. Teachers bring the frames into classrooms and ask students to mark the stars used for calibration, to plot the light curve, to feel how numbers turn into shape. The boundary between aesthetic and analytic softens. The sky becomes both gallery and laboratory, and young people learn that rigor does not smother wonder, it deepens it. Above all, our sense of belonging widens. To see a body from another cradle of worlds pass through our patch of sky is to feel that our neighborhood extends beyond the planets we memorized as children. We live in a region of a galaxy that is busy, porous, and full of traffic we are only beginning to notice. That realization is not frightening. It is humbling and hopeful. The message of these official images is that the universe is open for careful guests. When we look up now, we do not only seek constellations. We look for travelers and for the chance to welcome them with measured wonder. We began with images that seemed to resist belief, and we end with a story made steady by measurement. The official frames gave us 3 anchors. Morphology turned flicker into form, showing a body that likely stretches or flattens and flashes as it turns. Spectra and color translated hue into chemistry, hinting at weathered dust, modest ices, and grains shaped by long radiation. Dynamics tied the path together, a brief open arc sculpted by gravity and nudged by gentle, natural thrusts. The unbelievable did not fade. It became legible and therefore more wondrous. That is the quiet promise of science. The stranger the sight, the stricter the work, and the richer the reward. When a visitor arrives from beyond our sun's upbringing, it tempts us toward fast stories. But patience, calibration, and replication make a better tale, one that respects both beauty and truth. Hard to believe is not a dismissal here. It is a starting line. It challenges us to slow the footage, test the pipeline, fit the orbit, and let the light say what it says. Wonder grows deeper when it is earned, and the sky becomes a place we can know together. So, let us keep watching. Follow the updates, compare the next frames, and ask the questions that sharpen sight. What changed? What stayed? What repeats when the geometry returns? If you have a small telescope, join a coordinated watch and add a thread to the shared film.